But our next speaker is Marcus Klein from, I'll probably say it wrong, but Suragos?
Suragos, exactly, yeah.
Okay. And,
Very good.
And talking a little bit, not about deposition itself, but or coatings themselves, but quality control and some inline technology for quality control of coatings. So,
thank you. So my focus is to talk about quality control for conductive coatings, and those are applied in various industries, and I will give an overview of some applications that you know and maybe also some challenges that we also work with. The requests are pretty diverse because architecture low-E integrates into smart, into solar, it's all combined, so the stacks become more complex, and also the process options interact with each other. One layer system doesn't like to have this high heat, and the other one is the process is coming later. So there are different requirements which interact from topics which have been previously different and now merge into the same final glass application. So this is the outline. I will briefly introduce Suragos as a company. Maybe not everybody knows us yet. Then I will introduce the technology which is underlying of these solutions, and then I will run through the applications, explain some examples, and finally I will conclude with some innovations that I also want to share since we are here only every 2 years, and then I will summarize. First of all, Suragos. Suragos comes from surface Argus. Argus Phenoptilis is the guy from the Greek mythology with the 100 eyes, and we are supposed to see very well on surfaces, so Suragos, that's the name coming from. We are like 13 years old, company in Dresden, so not from Minnesota, but I'm sure there are many people from Dresden here as well. We have 50 people, and they all focus on eddy current monitors. Yeah, so we are doing eddy current monitors, and we do this sensors to measure emissivity, sheet resistance, metal layer thickness. These are the key applications that we have. Also, newer applications involve monitoring laser scribing processes, which are coming also into focus, or material removal processes, or measure line resistance of printed electronics. These are also applications. The fields are very diverse: architectural, automotive, smart glass, mirror coatings, and many, many more applications. The use or the quality control for conductive coatings is applied across the value chain. So it goes from layer deposition, where we have the classical sputtering, but also other like wet and printed processes where we have layer modification. Today we've talked a lot about glass tempering, and then we have layer removal processes which are also playing a role in some industries. Yeah. And I'm not sure if everybody is aware how eddy current sensors work, so I will give you a very brief introduction to it. The underlying concept is 100 years old, so we have an alternating current which we apply on a coil. This is generating a primary electromagnetic field, and if we bring a silver layer on ITO in this electromagnetic field, then we generate eddy currents, and those eddy currents generate a secondary field, and what we do is we characterize the secondary field. It's very fast, it's non-contact, and it's possible to well automate it, and we can use different frequencies, and this is allowing us to adapt penetration depth, sensitivity, and many more applications. Can be applied in different modes: top side mode, bottom mode, or transmission mode, and I already mentioned the benefits. What we need to know is that it can measure through conductive, through non-conductive films, and also non-conductive substrates. So we are just measuring through the glass, which is good for many applications. And when there is a multi-layer stack, we measure all the layers. Basically, the parallel resistance formula, which we know from the school, is applying here. So if I have one silver layer with 10 ohm per square, and I have another one with 10 ohm per square, I measure 5 ohm per square, and so on. If you ever want to calculate that, there's a nice calculator on our website where you can play with different models and also deduct the thickness from that. So it's a handy tool. Sheet resistance also correlates, at least in silver. There has been done some work on the layer thickness of the silver, but the most important part is that the sheet resistance correlates with the emissivity. And there's a limited frame where this formula can be applied, but basically it can be applied. This is a factor which you apply on the sheet resistance, and you get the emissivity for low E coatings. And there are some limitations that you shouldn't have too many cover layers on top and so on. But in general, the industry is applying this formula since many years. And here's also a chart that describes this easy correlation. There are 4 different testing types. Very briefly, portable single-point mapping and inline solutions. And inline solutions, there are traveling sensors, where we also do these integration kits for these traversing systems, and then the fixed sensor installations. The repeatable is key here, so I just selected 2 examples. One is TCO application, where we have 25 ohm per square, and one is a silver application, where we have this. So, but of course, there can be also challenges like temperature variations and so on, and these need to be addressed by certain things. And long-term stability is also very important. But now let's talk about the applications across the different applications. So first, let's start with architectural glass. Yeah. So the classic task that we support is the silver deposition. So basically, I will talk about this a little later in detail. Then we have the tempering, and then we have the final inspection, where typically optical and electrical and emissivity is tested. Environments is in vacuo and ex vacuo. And one typical concept is that after each silver deposition, there is a eddy current monitor, and it can be either one or many, 3 or 7 or 5, it depends. If people have the ability to control the sputtering process, if they have different elements, yeah, then it makes sense to have as many sensors as you have elements that you can control. If you have, if you cannot control this homogeneity, then one sensor is enough. Yeah. So these are typically the setups, and in the end, traversing systems is also one part. Another part is edge removal, which is a topic which is more upcoming for many reasons. Sometimes the conductive materials, ITO, or also the silver needs to be removed. And this technology can be also used to monitor whether there is silver or conductive material left. Yeah? So this is original measurement data. That is that we get color-coded signals, so not okay and okay material. So this is a rather new application, which is used then for laser scribing tools that use laser for removal or mechanical brushes to remove the coating. Other one is tempering. We talked about this earlier today. Basically, tempering is a rather complex process. The layers on top of the glass affect the heat distribution within the glass. So I have a different heat absorption from the top and from the bottom. And what we know is that the emissivity of the glass can change during the tempering process by 40%. Yeah? So in the beginning you have that, and in the end you have that. And this is also affecting how the glass absorbs heat and how it behaves. And it needs to be an even temperature absorption to have less stress, and many, many other effects play a role. And the idea here is to measure the emissivity of each glass which is running into the furnace, and to adapt also to the changes of this emissivity during the process. And it also offers potential for automation. And yeah, there are quite some applications here. This is for tempering. The easiest way is to just have a portable device to just check before you start, to just check what you really have. Because before and after tempering it's different. And there's some variation. Even with the same glass, you have quite some variations. This is what we observed. We did some tests on it. So Here are some examples before tempering and after tempering. And also we looked at the homogeneity before tempering and after tempering, and also on the drops that each glass is running. So here we have a drop of nearly 40%, 36%. Another application is, I'm not too sure, this is supposed to be a video. I'm not too sure whether we can play that. This is basically a measurement on the windshield. Okay. So one application is incoming good inspection. So it's looking what type of sheet resistance do we have for the windshields, and also to check in the production floor after unloading. Mostly the glass is already coming with conductive material, and then the bending process is following, and there are different reasons why the sheet resistance is measured in between. In automotive, there's also automotive mirrors play a role. Of course, mirrors get also more functionalized. We have displays in the mirrors today. If you drive taxi, you can see the price. You still have the reflection, so different functions going in. Or some even have a TV in there, so more and more conductive coatings going in here. So these are also an application. Another tricky application, which is not fully solved yet, is a printing of antennas on the windshield. It can be tricky to get the right quality. The problem is if you notice that something went wrong, it's too late. You have processed many other windshields, and there's one approach is to check the paste before. So we have an electromagnetic sensor which is characterizing the paste when it goes through a pipe, and we assess the electric and dielectric quality of the paste. And then later, there's a printing process, and then there's a drying and a firing process, and this trying to help when the paste is different. The paste qualities can be very different. It looks the same composition, how it can behave very different. And in the end, you don't know. Something is good for the printing process, the other thing is good for the drying process. So it's a need to be a trade-off. And this is something where other industries spend much more time on improving this. And I see also more applications in automotive antenna printing. Antennas are important. Also, we have the application discussed, mobile-friendly glass. So when you travel with a train and you don't have reception, we hate that. We want. And there's a solution by adding structures, even post. There's also a talk today about companies here that is adding this on existing trains afterwards. And the task is about monitoring the lines that are created into these, for instance, Germany, ICE. But there are also other trains that are getting this mobile-friendly glass. And so the structural integrity or the dysfunction of the glass, that is also a topic that is able to be monitored. Solar films, also metal deposition can be monitored in vacuo, ex vacuo. And the metal thickness is monitored here. There's solar glass, which is a big application. We see a lot of. Wednesday, I was still in Munich on the Intersolar. Big. It's growing. Solar industry is growing again. And here we have different applications. We have the transparent front contact, which is always tricky because it needs to be transparent and at the same time conductive. So you cannot always do more material on it, and then you get a better sheet resistance, then you lose transparency. So there's a sweet spot which needs to be found, and it's about efficiency. Point 1 is important, so they really fine-tune that. Some people also monitor the metal grid. Metal grids, meshes can be also monitored. So screen printing process of meshes can be monitored also after firing. And partially also before firing, just after drying. And then we have classical, the backside contact, for instance, molybdenum or some other combinations, which is rather easy to monitor, but also important for the functionality of the solar cell. Here's a few examples, what is also possible with the technology. We call this eddy current imaging. So basically each pixel is a measurement, and we we scan the material. We have scanning devices for lab work, and then we can plot the distribution in a histogram, or we can pull line profiles and analyze. For instance, this is here ITO. This is ITO, and this is ATSO as an example. These materials are also used in smart glass applications, of course. Basically, it's another function where you need to bring in current to achieve a function. So the layers are, again, for instance, ITO, and the setups are 3, 5, 7. It depends, again, on what you can monitor and what you can change in your sputtering process, for instance. 2 more applications: classical mirrors for home use. So here the unit is weight. Yeah, sometimes it's thickness, sometimes it's emissivity, sometimes it's sheet resistance, and here it's weight. But basically the same concept applies. So this is also a measurement which is relatively easy to do. And the last one is that I wanted to mention is display, of course, and touch panel sensors, where we work with all sorts of material, metal meshes, nanowires, carbon nanotubes, also metal films, ITO, and the setup really depends on the process which is used there. I guess I missed some of the applications because there are many more. We also work with heated glass. This is an application, home appliance. There are some reasons. There are medical applications, and there are many, many more. And yeah, sometimes we are looking for more of these applications. So if you have some ideas or some requests for working with conductive films, then please approach us. Last but not least, I wanted to share 4 more innovations which we set up in the last years since the last GPD. So one we call semi-vac sensors. Basically, sometimes we have narrow spaces where we have not much space to put our sensors in. So we hide the sensors with a very small coil in here, and the rest of the sensor is outside. So this is semi-vac because only a small part is in the vacuum. It helps to integrate in certain environments. Difficult environments are also shown here. So we have developed an extra small sensor which is applicable. This is just a sensor tip. It's applicable for hot environments, and it's also applicable for chemical environments. So we could put even the sensor into electrolyte. So we can do plating monitoring. So a bunch of applications are possible with that. So this is here for ITO characterization, and there are also annealing tests. There are more information. FEP, I think, is having a talk at some conferences about it. And another application that we tested with FEP was to create a vacuum traverse. So typically traversing systems, we in the past only used X-vacuo, but now we also tested our in-vacuo integration set there. Can be useful for some applications. And a couple of years back, we also did an ultra-thin glass project where we integrated our sensor into a tool which I think could handle 40 micron thick ultra-thin glass, which was also quite unique. These were the key points that I wanted to make today. The summary is, I didn't talk much about Suragus, but we have a multi-diverse workforce, seven from 7 different nations in Dresden. The eddy current technology is non-contact, very fast. The measurements are done in emissivity, sheet resistant, metal layer thickness that we monitor, and the innovations I have shown that we are able to work in hot environments, in tight environments, and very different applications. The applications that you have seen here, I mentioned some of that in architectural glass, silver deposition, the tempering, layer removal, layer structuring, and then smart glass, solar glass, heating. So much applications are upcoming, and it's exciting to observe that, to see here what is new, to discuss the new processes, to discuss the new materials, and discuss the new challenges. And there's more to come, and I'm very much looking forward to it. Thank you.
Thank you very much. Do we have any questions? Well, people think I have a question. So thinking about silver deposition, low-E coatings or whatever, is there a minimum thickness layer? Or,
yes, good question. So the theory says that when the islands start to be connected and the current can flow, then we get a reading. So the alternative approach is 4-point probe, where you have a contact. And in 4-point probe, I think you say from 5 nanometer, you get connected islands where you can get a reading. In the eddy current, at least the book says it's 2 nanometers. Sometimes the islands form from 2 nanometer. We are also applying this technology for graphene, a monolayer of graphene. So it's not about thickness, it's about the ability of the current to flow, and then it can generate electromagnetic fields that we can pick up. Yeah.
Over a certain area.
Yeah,
right?
over a certain area. Yeah.
That ties back into the earlier talk about island coalescence. We had an
yeah, it was very nice, very interesting. Yeah.
What is the measurement spot size of the eddy probe?
Also good question. So technically, we have spot sizes from 1 millimeter to 100 millimeter. Yeah, so the smallest coil that we use is 875 microns wide. But you have a very small field. It doesn't go far away. Yeah? So in the glass applications where we typically have large distances, sometimes like 40 millimeters, when we have thick glass coming through, then of course the measurement field, we have the rule of thumb 2 times gap. Yeah? So if I have a 20 millimeter gap, then we have a 40 millimeter measurement spot. But we also have spot sizes down to 1 millimeter, 3 millimeter, which we use, for instance, for the scribing monitoring. Yeah? So we want to precisely look at where the scribe is and see whether it's separated or not. So we can design that depending on the application. Yeah.
Any other questions? Well, if not, thank you for a very interesting talk. And with that, we'll be moving on to the coffee break.
Thank you.